So many in the community have done core for core and clock for clock benchmarks of Zen versus Skylake, or at least they think they have. However, I don't feel that they actually have. The reason for this is Intel's Ring Bus and AMD's Infinity Fabric runs at different clock speeds, and those haven't been accounted for. So in this video, I'm going to be doing testing on Zen and Skylake in a core for core, clock for clock test with both SMT enabled and disabled, with the Ring Bus and Infinity Fabric running at the same bandwidth. But before that, I'm Hakaru, and this is the Ultimate Computer Scientist. So this video was just going to be a single video for all of the testing. Unfortunately, I will have to do two videos for this, as I'm having massive issues in game testing for two reasons. Lots of driver issues, and my only solution is a new install of Windows with a fresh driver install. Also, I'm no benchmarker, so getting benchmarks sorted took a while, and the game testing is massively delayed. That's why I'm doing two videos. In this one, I'll just be doing non-rendering benchmarks. So let's get into it. The CPUs that I'm testing are an i7-6700K and a Ryzen 7 down-cored to 4+0 config. The reason it's in a 4+0 config and not 2+2 is because, as I discovered in my cache bottlenecks video, 4+0 disables half of the cache, and that will bring the total L3 cache of the Ryzen CPU to the same as on the Skylake chip, and that means we have already counted for the L3 cache differences. Both the CPUs were tested at 4 GHz, and I have results for the CPUs with SMT enabled and disabled. Also, and most importantly, the thing that really sets this testing aside from everyone else's is I have taken into account the bandwidth differences between Skylake's Ring Bus and Zen's Infinity Fabric. Both the Ring Bus and Infinity Fabric are 32 bytes wide. However, the Infinity Fabric runs at half of the memory speed, which is usually in the region of 1.5 GHz, and the Ring Bus typically operates at over 2 GHz, typically providing in the region of twice the bandwidth of the Infinity Fabric. Not only that, but here, the Zen CPU is effectively two Skylake CPUs attached to the same bus in an octa-core configuration, effectively giving an octa-core Zen CPU in the region of a quarter of the bandwidth of the Skylake CPU per core. So this testing is normalizing that. And to do that, I need to lock the Infinity Fabric speeds to the Ring Bus speed, and as I've down-cored the Zen to 4 cores, we will have the same bus bandwidth per core on both CPUs. So to do that, I got my high-speed memory kit rated for 3066 MHz and clocked it to 3600 MHz. This meant that the Infinity Fabric would be running at 1.8 GHz. I chose 3600 MHz because it's the fastest that I can really get my Ryzen 7 and my Skylake CPU to run stably. In the Skylake CPU, I set the same memory speeds and timings. The timings were 16, 18, 18, 36. So now both CPUs have the same memory speed. All I have to do is set the Ring Bus speed to 1.8 GHz to match the Infinity Fabric. So I went into the BIOS and dropped the Ring Bus's clock speeds to 1.8 GHz and restarted the machine. So now we have two 4-core CPUs with the same amount of L3 cache, the same bus speed, and the same clocks, just one is Skylake and the other one is 1st Gen Zen. So now the tests can begin. The tests that I ran were Cinebench R15 and Geekbench. I was going to do GPU Pi, but unfortunately, it couldn't detect the Zen CPU, so I couldn't test it. If I can fix it for part 2, I'll do it then. So let's get into the tests. First, with SMT enabled, so both CPUs have 4 cores and 8 threads. In Cinebench, the Skylake CPU got 814 points, against Zen's 894 points. That's a 9.8% lead that the Zen CPU has, which doesn't entirely surprise me, considering, in a previous video, I showed how clock for clock, a Ryzen 5 2600X at 5 GHz just edged out a lead on an i7-8700K also at 5 GHz. A real example is these two Cinebench runs, a Ryzen 5 2600X at 5 GHz with 6 cores and 12 threads up against an i7-8700K also at 5 GHz, 6 cores and 12 threads, with the AMD CPU pulling ahead by 1.5%, well into their run-to-run variance, effectively demonstrating the same IPC. In this test then, surely if I could clock the Infinity Fabric to an unheard of speed and chop down the ring bus to a pretty low speed, then we ought to see a little more performance on the Zen CPU and a hit to the Skylake CPU, and that's what we've seen here. So it's not surprising to me that Zen is now ahead in this test in per clock performance. Next up is Geekbench, where the Skylake CPU got a single core score of 4,951 points against the Zen's 4,719 points. So in this case, the Skylake CPU has got a near 5% performance lead over the Zen CPU, which might be surprising considering how gimped down the Skylake CPU is and how buffed up the Zen CPU is. But I'm again not overly surprised at this benchmark. It's just a linear, crunch a bunch of numbers and tell me when you've finished benchmark, and as such, there isn't much communications across either the Infinity Fabric or the ring bus, and as a result, the performance per clock hasn't changed much as a result of the changes to the bus speeds. Now the most interesting thing here is when we look at the performance breakdown for this test, i.e. floating performance, integer performance, and memory performance. So in the integer and floating tests, the Skylake CPU scored 4,968 points against Zen's 4,374 points for integers, and 4,771 versus 4,261 in floats. In both cases, that's near a 13% performance improvement Skylake has over Zen. That's quite the jump from Zen beating Skylake by near 10%. This shows us that it's actually a design feature of the Zen core that is limiting performance here. The weak part is that AMD splits their cores into two separate pipelines, one solely for integer arithmetic and one solely for floating point arithmetic. This allows for easier core development, as you have two independent pipelines to develop, and so can be developed by two separate teams with little dependencies between each team, and it also makes scheduling easier for the execution units as you are not mixing floats and integers together, and for the most part, in real-world workloads, there are no drawbacks. Where there are enough floats and integers to fill both pipelines, you find the full bandwidth of the core can be utilised. This explains the Cinebench score, where Zen is ahead by a statistically significant margin, showing us that Zen cores do definitely have the bandwidth to match and even beat the Skylake core. However, that's in a mixed workload where there are floats and integers operating together, which can take advantage of a wide pipeline. However, when you're doing a test with only one type of workload, such as in Geekbench, where there are separate integer and floating point tests, then the Skylake rarely comes ahead, as only one of the Zen pipelines is being utilised at any one time, where the Skylake CPU can have its execution units work on both, so when there is only one type of workload available, the Skylake's core is still more utilised. So considering all this, I'm not too surprised why the Zen CPU got hammered by Skylake in the floating and integer tests. However, one thing that has always interested me, and as you can see in other reviewers' videos and blogs, is that Zen always seems to have a memory bandwidth advantage over its competing Skylake part.
Right, so let's get to the results. Starting with the sustained memory bandwidth test, here we see that the first and second gen Ryzen CPUs are very similar with a bandwidth of around 39 GB per second. Meanwhile, using the exact same memory, the Coffee Lake CPUs are limited to around 33 GB per second, and this is a 15% reduction in bandwidth when compared to the Ryzen CPUs.
And that was interesting, if the Skylake part had the faster ring bus than Zen, and so surely the core's bandwidth to the memory controllers would be wider for the Skylake part. However, I believe I have found the reason for the higher memory bandwidths of the Zen parts. Looking at Dr. Agner Fogg's CPU architecture breakdown that I've referenced in the past, Dr. Fogg shows that the Skylake core has two load units that also do address generation and a single store unit. These execution units are the execution units that are used to execute memory access instructions. Now looking at the Zen's execution units are a little more complicated. So Zen has two AGUs for address generation, which allow for up to 2 loads per clock, the same as Skylake, and also a single load and a single store, together which may be lower than Skylake. However, there is actually another memory access unit in the core. According to Dr. Fogg, one of the other FPUs in the core can do memory writes, which allow for the Zen core to do up to 1 memory read and 2 memory writes per clock. This configuration may actually be advantageous to the Zen core in memory-intensive workloads. Not only that, but also remember that the ring bus goes through the L3 cache, whereas the Infinity Fabric doesn't. That means the L3 cache bandwidth is also used by the ring bus, which could reduce the available bandwidth for memory accesses. So all of this together makes it rather unsurprising that the Zen CPU comes out with just over a 10% lead when it comes to memory score, which is Skylake's 5,245 points versus Zen's 5,846 points. Interestingly, this lead is made solely by memory bandwidth, as Skylake gets 22.3 GB per second against Zen's 30.6 GB per second, so over an 8 GB per second lead Zen has in bandwidth, which is an immense 37.2% lead for the Zen CPU. And remember, both CPUs are using the same memory kit at the same speed with the same timings, and also note that this isn't a latency issue, as we're having latency tests too. Now, I was also interested in seeing how latency would change with both CPUs using the same memory speeds and had the same bus speeds. So the Skylake CPU got a memory access time of 62.2 nanoseconds against Zen's 73.6 nanoseconds, so it appears there is an additional 10 or so nanoseconds found on the Zen CPU. Now, looking at AnandTech's article on Zen+, they say that Zen+ ought to get about an 11% improvement in latency to memory at the same clock speeds. So I worked that out to mean if I had a second gen Zen CPU and did the tests again, I ought to get in the region of 65.5 nanoseconds of latency. This closes significantly on Skylake. Now, if you think the latencies here are interesting, there are certainly more surprising results for the disabled SMT ones. Anyway, long story short, Zen vs Skylake in single-core Geekbench has Skylake narrowly ahead. Skylake demolished Zen in pure floating point and integer workloads. However, Zen demolished Skylake in the memory benchmark. Looking at the multi-core benchmarks now, and things really get interesting. The margins overall stay the same. Skylake is still in the region of 5% ahead of Zen. However, looking under the hood, and things get a little strange. So looking at the integer workloads, before, in the single-core tests, the Skylake CPU is near 13% ahead of the Zen. Now it's only 2% ahead. That's an absolutely enormous drop. Looking at the float workload, it's now only 7% ahead, whereas before it was 12% ahead. Again, a huge performance drop. But it's not only the Skylake CPU that has lost its lead. When it comes to memory scoring, before Zen was 10% ahead. Now that lead has shrunk and it is only 2.5%. The reason for this narrowing of the gap, I believe, is that with all the cores active, the bus bandwidth may be the limiting factor to feed all of the cores, and as both CPUs have the same bus speed, the performance is most the same. This is only a theory, and is something I'd like to test out in the future, but this does make sense, as in the memory benchmarks, when the CPU cores get quadrupled, the bandwidths aren't even nearly quadruple. The Skylake CPU only gets a 50% memory bandwidth improvement, whereas it gets a 400% core bandwidth improvement. Zen does even worse, coming off with only 27% memory bandwidth improvement. Lastly, something to note is that the memory latencies are hardly affected by the shift from single core to 4 cores. Now, looking at the theoretical achievable memory bandwidth a dual-channel memory kit running at 3600 MHz has, this is a bandwidth of 57.6 GB per second, so neither of these CPUs are reaching the limit of the DDR bus. Also, the buses have the same bandwidth. The Infinity Fabric runs at half the memory speed, however it's twice as wide. This means it's got the exact same bandwidth, and as I have adjusted the ring bus clock to match the Infinity Fabric, as they're both 32 bytes wide, the ring bus is now also running with the exact same bandwidth as the 3600 MHz DDR interface. So both CPUs aren't exactly out of memory bandwidth, so I reckon there are two possible reasons for the poor scaling, and neither of these are exclusive to each other. So one of them is high crosstalk across the bus. This bus is used for enough things that it could be zipping away at that 57 GB of bandwidth. This also helps to show why Skylake is behind Zen, as Skylake's cores have to go over the ring bus to access the L3 cache, which further hits the bus's available bandwidth. The second reason is pipeline stalls for memory access instructions. The cores are likely to be at their maximum memory instruction throughput. These CPUs aren't exactly built for nothing but memory accesses, and as such, their memory access related instruction units make up a small part of the total execution units across the core. I can also say that these instructions are very well fed into the cores, and there were no front-end stalls caused, as you will see when I disable SMT. The memory bandwidth stays the same, showing that SMT doesn't improve bandwidth, and as such, there aren't any branch mispredictions being made. So let's turn off SMT and see how things change before I wrap it all up. So going back to Cinebench R15 with SMT disabled now. Remember before, Zen was approximately 10% ahead. That lead has now shrunk to just under 3%. So when people and AMD claim that their SMT implementation is better than Intel's, this sure is evidence to support that, as when I disable SMT across the CPUs, Intel catches up. However, I don't much believe that we should accept on face value that AMD's SMT is better than Intel's, or it wasn't until Spectre Meltdown came out anyway, but that's something for another video. All we need to know is SMT is disproportionately improving AMD's performance here. Kind of. I'll explain later. Looking at Geekbench single core, the margins are exactly the same overall, but again, under the hood is interesting. So the margins are the same, however, with SMT disabled, Intel's integer performance lead has extended as before. Before, Intel had a near 13% lead. Now, that lead has expanded to just over 16%. Also, the flow performance lead has increased by just over 1.5%. That's interesting, but what's maybe even more interesting is Zen's memory performance lead has also extended. Before, AMD was around 10% ahead, and now with SMT disabled, AMD is 15% ahead. Now this performance improvement comes not from bandwidth, but from latency. Neither architecture see much of a bandwidth improvement with SMT disabled, and as I said before, the memory access instructions are very well scheduled and predicted, and there are comparatively few execution units for memory accesses, so we won't see much of an improvement in memory bandwidth as a result of SMT. So why did AMD get a 15% lead then? Well, it's about the memory access latency. For Intel, SMT on or off doesn't have any effect on memory access times. However, really interestingly, disabling SMT for Zen CPUs nets an absolutely huge latency improvement. With SMT, the memory latency was 73.6 nanoseconds, whereas without, the latency was 66.7 nanoseconds. That's about on par with Intel, and Zen Plus would be even better. Applying the theoretical 11% latency improvement to Zen Plus would theoretically lead to a memory latency of 56.2 nanoseconds, far ahead of Intel at this point. Now of course, I can't actually test this as I don't have a 2nd gen Ryzen part, but this is a very high speed memory kit, and with this kit on 1st gen Zen, I have been able to get below 70 nanoseconds before with SMT enabled, so below 60 on 2nd gen could be possible, particularly without SMT. So now the big question is, why does SMT cause additional latency for AMD and not Intel? Well, I believe I have an answer for that. The reason I believe to explain all this is that Intel got hit by Spectre Meltdown. But why could that have an effect on memory performance regarding SMT? Well, one of the issues with Intel's implementation of SMT is that the threads were poorly partitioned, and as a result, when Spectre Meltdown dropped, Intel had to disable multi-threaded execution of memory access instructions across the 2 hardware threads, as one of the vulnerabilities were that one thread could access memory reserved by another thread. Also, speculative execution of memory accesses were disabled to counter Spectre and Meltdown. In other words, Intel's traditional SMT implementation was a security risk. And do you know what market segments will be completely unaccepting of anything less than perfect security? The servers and data centers. So looking to Adored TV's video about Skylake, Intel's cascading failure, he looked into the possibility of Intel disabling SMT on their server processors when prompted by a piece of an Anantech article written by Dr. Ian Cuttress.
article again, and something I hadn't considered but was picked up by the author, Ian Cutress, who said, Intel is still keeping a lot of details for Cascade AP under wraps for now, but what we do know is some high-level specifications. Cascade AP processors will be up to 48 cores, possibly with hyperthreading. They wouldn't disable hyperthreading on these parts, would they? I hadn't even considered it, but it would surely help a huge deal with power consumption.
Now, Jim's investigation showed overwhelming evidence to suggest SMT is going to be disabled.
But as anyone following my channel knows, the thing about presentations is they usually end with footnotes giving further details on how the systems were set up. And given this is Intel, let's just skip right to the end of this and configuration details. Okay, so Linpack AMD EPYC 7601, it's on a Supermicro motherboard using two AMD EPYC 7601 processors with SMT off. Now, to be fair though, Linpack should be benchmarked without hyperthreading, and that's what they've done. It's just a little bit curious that they decided to show the Linpack result in this particular case. Now, what about this DL inference? And once again, we see a 2-socket Intels Zen Platinum 8180 CPU with hyperthreading disabled.
Now, Jim's analysis was that SMT was disabled for power reasons. I disagree. Power will be reduced and could be a positive side effect, but I firmly believe it was used to ensure security of shipping processes, as no data center would go near Intel's SMT. It was the only way to effectively counter Spectre and Meltdown, along with disabling speculative execution for memory accesses. So with all that talk about Intel's SMT, how does this make AMD's SMT better? Well, I'll tell you. AMD was never affected by these problems, were they? They largely avoided Spectre and Meltdown, which means that their SMT was not vulnerable. That means that with SMT, AMD's implementation is correctly isolating the memory spaces of the two threads, and this takes time, clock cycles, so when SMT is disabled for the Zen CPU, this partitioning doesn't have to take place. As such, the work item can get through the pipeline quicker. That's why, if you remember back to Zen's launch, reviewers were discovering and testing that Zen CPUs saw performance uplifts in games when SMT was disabled. Now, turning to the multi-threaded Geekbench tests with SMT disabled on both CPUs, Intel's lead actually improved by 5%, from 5% to 10%. This is down solely to the issues Zen faced regarding splitting the integer and floating pipeline. So the margins there stayed mostly the same, with a 1% performance lead improvement in the best case. And as I said before, the memory access instructions weren't bound by scheduling. Using SMT didn't have much of a performance improvement for memory bandwidth, and as such, AMD's previous lead before, which was memory bandwidth, wasn't extended again. This is why Intel gains a small amount overall, but interestingly, again, the Intel CPU in multicore didn't see a memory latency change throughout any of the tests. However, AMD with SMT off did lose some of its lead, but it was still statistically significantly faster than even the fastest access times allowed by having SMT on, showing that SMT really does increase memory access times for AMD CPUs. So when dropping bus clocks of a Skylake CPU to meet that of Zen CPUs, the Skylake CPU is disproportionately affected. In the majority of workloads where the work types are mixed, such as Cinebench in this case, Zen does pull ahead by a statistically significant margin, particularly with SMT enabled, where Zen was ahead by 9%, and this is first gen Zen as well, not Zen Plus. Not only that, but this also has a negative impact on memory latency for the Skylake CPU, which can only be further impacted as the core count on the ring bus increases. So an 8-core Skylake CPU, e.g. 9900K, clock for clock, ought to have even worse performance as the memory latency only increases as you add more cores to the ring bus. Not only that, but you can see one of the other reasons for this disproportionate drop in performance for Intel is that if the Skylake cores need to access L3 cache, they have to go over the ring bus, which has been slowed down for this testing, whereas for Zen, the L3 cache runs at core clock speeds, and each core has its own dedicated 32-byte wide interface to the L3 cache. So for L3 cache accesses, a single Skylake core we'll have to go through other cores and the North Bridge to access the cache on the bus that was running at 1.8 GHz, whereas the Zen core was going straight to the L3 cache over a bus running at 4 GHz, and things would only get worse if you added cores to the Skylake CPU. Next, for separated workloads like pure integer or pure float workloads, Skylake takes the lead quite noticeably, as the Skylake's core's backend is more flexible with execution units that can perform different tasks, helping core utilization. The other interesting thing here is seeing how SMT affects memory accesses, and as such will affect all I/O to the processor, even between GPU and CPU. So whilst AMD claims a better implementation of SMT, I don't fully believe it. I believe the reasons why AMD gains ground over Intel when both have SMT turned on is not that the SMT itself is faster, because it isn't, it's slower. I believe AMD's SMT provides a better performance improvement because it allows for better utilization of the execution units. This is also something to keep an eye on, as with Zen 2, the core will have twice the floating bandwidth. Anyway, that's it for this video. This is only part 1, so I'm going to keep more for the next part. As I said, part 2 will have the rendering benchmarks, like games in it. I think it will be interesting as gaming is where Skylake usually shines. Also, one last thing is, I'll leave a link in the description for the resources that I've used as evidence in this video. That's all for now, and as usual, I hope you've enjoyed the video and learned something.